Okay, we are in 5.5. This will be your last section before a quiz. So we've got some review coming around. And what we are going to talk about in this section, we're going to leave integrals for a little bit, but talk about them, but we're not actually going to be integrating. Area under the curve. Remember, when we were doing integrals at the beginning of the year, when we defined integral, it was area under the curve. And up until today, you had counting squares, and you had the trapezoid rule, finding the area of the trapezoids under. Today, we're going to be using rectangles and tie it into our integrals that we did for 4 days. So before we get into the process, because these are going to be approximates, because rectangles aren't going to fit curved shapes perfectly, there's 3 different kinds of sums we can find. The first one's called a lower sum. A lower sum is just an underestimate for the area. And what happens is all of our rectangles are going to stay under the curve. So if we look at, let's say, this function here, which is increasing concave up, and if I wanted the area from A to B, and let's say I was going to break that into 3 rectangular regions, all the same width. If for rectangle 1, I need one of these edges, either this point or this point, to be my height of my rectangle, and because I want a lower sum, I'm going to pick the lower point. So I'll let that be my height and create this rectangle here, and I'll be able to find the area of that because I'll know the height from the function, and the width I'll be able to figure out when I actually have numbers down here. So I'll go height times width, and that'll give me the area. For rectangle 2, I want to use this left edge again, because that's what's going to keep my rectangle under the curve. And for rectangle 3, I'll use the left edge. And so it's an underestimate because there's space above the rectangles that we did not include in our area. Now, for a lower sum, is it always going to be the left edge? Well, the answer to that's no. Say the curve looked like this, and I had a region from A to B, and I wanted 3 rectangles. So now if I look at rectangle 1 here, I have a choice of the left edge or the right edge. Well, the right edge is what's going to keep me under the curve. So I'd use the right edge as my height, and then the width. The right edge as my height here, and then the right edge as my height here. So don't automatically think lower, I'm going to pick the left edge. It could be the right edge depending on which way the graph is concave up or down, and increasing or decreasing. So you have to look at the graph. Okay, we're also going to be doing upper sums. And I think you can guess an upper sum is an overestimate for the area. Because when we choose our rectangles, when we choose the height, each rectangle is going to be above the curve. So we'll look at the same 2 functions. We'll go from A to B. And we'll make our 3 rectangular partitions. So we'll chunk this up into 3 rectangles. Make our dividers. All of our dividers are the same width apart. So now if I want an upper sum, when I look at this first region and I want to turn it into a rectangle, I'm going to choose the right edge, because that's what's going to make my rectangle go above the curve. So I'll be including this area above the curve, making it an overestimate. Same thing here, the right edge and the right edge again. Something like this, if I want an overestimate, I want the left edge to be my height, the left edge to be my height, and the left edge to be the height. So you can see the heights of our rectangles are going to be determined by the function itself. What's this y value? What's this y value? What's this y value? And then the last kind of sum we're going to be doing, and it's the same no matter what, it's called the midpoint sum. And here there's no steadfast rule whether it's going to be an over or an under. It depends on the steepness of the graph. So we only need to look at one graph then. So still doing 3 rectangles. So if this is going to be my rectangle 1, I want to pick the midpoint of this distance. So if I pick the middle, that's the corresponding y value that I want to use. That will be the height of my rectangle. So you can see I miss a little bit of the area here, but I gain some above here. So which piece is bigger all depends on how steep this graph is. So it's hard to tell whether it's going to be an over or an under. It can be either one for different functions. So same thing here. Pick the middle of your rectangle. Let that function value be your height. And then the middle again. Now, sometimes if it's, say, a graph that increases and decreases, like say sine or cosine, it won't be a uniform left edge, left edge, left edge, or right edge, right edge, right edge. You might have to flip-flop your way through there. So if I look at a sine curve, and let's say I go from A to B, and I want 3 regions here, for my first rectangular region, let's say I wanted, let's go with an upper sum. I would pick, no, I want a lower sum. I'll go lower. So if I want a lower sum, I'm going to pick the left edge for this first rectangle, because that's what's going to keep me under, left side. But now for the second rectangle, because now I've gone from increasing to decreasing, I want the right edge. And then I'd want the right edge. So if you've got a graph that increases and decreases, you're going to have to hand pick all the way through left edge or right edge. Okay, this process of finding the areas of rectangles and adding them up is called a Riemann sum. Riemann sum. This approximates the area under the curve using rectangles. And this is what his formula looks like. It looks kind of complicated, but it's really kind of easy, super easy actually. Riemann, R for Riemann, a rectangle too. N is the number of rectangles you're going to have, or the number of partitions. The Riemann sum is equal to K equals 1 to N of F of C K times delta X. Okay, looks impressive, but it's really not bad. What we're talking about here, if we had a function let's say we were going to go out to 3, and it wanted it to be a lower sum, I would be using this x value here. This would be my first x value, because that would give me the lower sum. This would be my second x value, so I call it C2. this would be my third x value, third and final, and I call it C3. So what his formula says is give me the function value at each of those C values. So I'd plug this x value into the function to see what the corresponding y is. That's going to give me the height of my rectangle. And if I know the distance from here to here, I can figure out this width. So the delta x, and they're all the same, we keep it uniform, the delta x is giving you the width of your rectangles. And his formula says multiply height times width, that's giving me an area. The sigma says add them all up. And then what he proved was as we decrease this width, and as we decrease the width, we increase the number of rectangles. And if we keep finding these sums, they limit in on a number. Okay? So the approximates, the smaller you make them, the more accurate you are. The value that they're limiting in on is the integral value. So the integral from a to b of f of x dx is the limit as delta x approaches 0 of the lower sum or the upper sum. The limit as delta x approaches 0 of the upper sum. These two approach each other as this width gets narrower and narrower and narrower. So in the next section, we're actually going to be calculating integrals without doing this approximate stuff. So it's the last time you have to approximate the area under a curve. So I'm going to take you through one example. We're going to use the lists in the calculator to make your job a little bit easier. Not that this is difficult, because all we're doing is finding areas of rectangles and adding them up. But because there can get to be a lot of rectangles, we'll let the lists keep it organized for us and do a lot of the work for us. And then after that, I'm going to show you a program that you can use too. So you have to know both ways. The by hand is with the tables or with the lists in the calculator, and then the program comes at the end. So we're going to do this one example 3 ways. We're going to do an upper sum, a lower sum, and a midpoint sum. So we want to approximate the area under approximate the definite integral by using Riemann sums. So we're going to look at the integral from 1 to 4 of 1 over x dx. So we should have a sketch of it because we're going to need to know whether we're using the left edge or the right edge. So my calculator is here. Y equals 1 over x. I'll do a zoom 6. And I'm only concerned about the 1 to 4 here. I can see it's scooping down. It's all just really close. I'd have to change my window to make it look a little bit better, but I can get the general idea from here. So the graph looks like this. Scooping down here from 1 to 4. Okay, the first one we're going to do is, let's go with a U6. This means we want to find an upper sum with 6 rectangles. So upper sum, 6 rectangles. So we're going to keep our work organized in a table. It's going to be a 3-row table. And it needs 6 columns. All right, so starting at 1, finishing at 4, the first thing we need to decide is how wide our rectangles are going to be.